Let's say we want to simulate phenomena in nature. There are always spatial scales involved. For example, think about ocean waves circulating the Earth. Think about seismic waves propagating around the Earth, and you see this phenomena actually behind me on the screen. Seismic waves propagating around the Earth. If you want to understand these phenomena, you need to discretize these waves in an appropriate way to make the simulations accurate. Now let's make an example. Seismic waves are actually observed for earthquakes that are far away with frequency up to 1 hertz. The speed with which these waves are propagating is at least on the order of 3 kilometers per second. Think about what that means. That means actually this is about 10,000 kilometers per hour, which is actually quite fast. That's about the speed with which satellites go around the Earth or rockets go to planetary objects. Now, to understand the wavelengths involved, we need a very fundamental equation that we use all over the course, and that's the relation between velocity, frequency, and wavelength. So C is the propagation velocity is equal to lambda, the wavelength, times the frequency. Now, given these numbers, we've said 3 kilometers per second at 1 hertz. That's a very simple problem. The wavelength of the wave will actually be 3 kilometers. So if we want to discretize such a wave, and we now make a simplification, let's assume this is a monochromatic wave, a sinusoidal wave. We would like to discretize this wave with about 10 grid points per wavelength, and you see this here, what I mean by that. And again, that's an extremely fundamental concept, how many points or cells we need to discretize such a wave. In this point, it's 10 grid points per wavelength. And now we ask the question, well, how would we have to discretize the entire Earth if we would like to simulate waves at this frequency with this wave speed propagating through the Earth? Let's do that. So we said a propagation speed of 3 kilometers, 10 grid points per wavelength. That means 0.3 kilometer grid spacing or grid distance, or actually side of a cube cell, a cubic element that we need to discretize our phenomenon. Now, what does that mean if we want to discretize the entire Earth? The radius of the Earth is 6,371 kilometers, and the volume of the Earth would be 4/3 pi times r to the power of 3. Now that's a very big number, as you can imagine, and we need to divide the entire volume of the Earth by the volume of our unit cell, the smallest grid cell that your computational cell, if you want. And that's 0.3 kilometers in brackets to the power of 3. Now, if you make the calculation, you get a very large number. That's actually 4 times 10 to the power of 13. And if you multiply that with 8 bytes, one as a double precision number, that's the memory space you need for one number, you get at a 420 terabyte memory for one field, for example, for the density model or a velocity model of the Earth. Wow, that's a large number. That's a very big number. And that immediately makes it obvious that that's nothing you can simulate on your smartphone, even on your laptop. This is something that's even too big to run on the largest supercomputers, or let's say we're just around the corner where something might be possible with these kind of memory requirements. So that's the reason why we also need to talk a little bit about parallel computing, even though that's important to note. In this course, we'll focus on 1D, at best, two-dimensional 2D solutions, because otherwise we would have to have a course that goes much beyond 7 weeks. So a few words on dimensionality. I mentioned that in this course, actually we focus on providing or developing solutions for the one-dimensional case, the one-dimensional wave equation, which of course then is defined on a line. We also develop some, at least for the finite difference and pseudo-spectral methods, two-dimensional solutions. That an example is shown here in the XZ plane. We have a full coordinate axis here, or full coordinate system, and that has some consequences that we discuss later during the course. But of course, the world is three-dimensional, and you can see that here. If you're in 3 dimensions, you have to discretize all the whole entire three-dimensional domain. Now let's look at some concepts of meshes here. In 1 dimension, that's of course very, very simple. So let's look at it in 2 dimensions. You can see here a regular grid. So you have equal grid spacing in the X and the Z direction. That's an XZ grid. It's a 2-dimensional regular grid. And there's already a problem. For example, think about a structural discontinuity. It could be a layer inside the Earth that's actually curvilinear and goes through the grid. And in the top, you see there is no way out, basically, that you then have a blocky representation of that interface. This can be fixed by, for example, making use of a triangular grid that you see in the bottom. So in that case, you can actually honor the discontinuity, but from a mathematical computational point of view, actually that's an overhead, which we will also see later. Another approach that helps in these situations where we want to discretize around curvilinear discontinuities is the so-called octree approach, and you see an example here, is that you refine your mesh in the area of interest, in that case the interface, and that's another very elegant way of solving the problem of internal complex geometries. In 3 dimensions, I just give you an example here. You see a mesh that's actually discretizing a volcano. In that case, this is the Merapi volcano in Indonesia, which has a very complex topography. In that case, it's actually discretized with so-called tetrahedra. So it's a tetrahedral grid that has some advantages concerning the mesh generation. Other possibilities are discretizing with hexahedral elements, which is a little more complicated, but we're not going to deal with this here. But what I would like to mention is that in many situations, if you have complex geometries, that this might be applied to, for example, also in engineering, if you would like to understand, for example, the airflow around the wing of an airplane or a rocket, that's very complicated. It requires to generate complicated computational meshes, and that also can be quite difficult, but that's not something we're going to deal with here. So eventually we want to discretize propagating waves, probably away from a source point. They might be far away, so they're almost planar waves. In 1 dimension, actually, will always be plane waves. And we need to find ways on discretizing those wave-like phenomena. They might be sinusoidal, they might have an arbitrary waveform, and let's just look at some fundamental ways of achieving that. We've actually encountered one before, and that's simply thinking about the finite difference method that we encounter in the next week, is simply we employ a certain number of grid points per wavelength. Here you can see a sinusoidal wave discretized with a couple of points. And again, the question on how many points per wavelength we require for a particular method will be extremely important. So this is something we call a grid method, where we actually simply divide or take a number of grid points for a particular characteristic wavelength of the wave field. Another approach that we will encounter in pseudospectrum method is, and that's illustrated in this figure here, is that we actually describe the wave field, or here it's a Gaussian shape function that might propagate away from the source by a superposition of some basis functions. And if we employ Fourier type method, these basis functions are of course sine or cosine functions. And you can see those in the these dashed lines. These are basically the basis functions appropriately weighted and summed up. They actually will lead to the Gaussian-shaped waveform that you see in this figure. The finite element type discretization is yet different in the sense that you're dividing up the spatial domain, as indicated here, into elements. And then actually inside these elements, you approximate the function with, in this case, linear basis functions. So actually in this case, then the approximate wave field is known at all points, which is different to the finite difference method, where you know the function only in the numerical approximation only at these specific grid points. So in the linear finite element method, as the name says, inside the elements you have only a linear description of your physical phenomenon, in this case, the wave field. Now the spectral element method, that will be the last method we will encounter in this course, will be actually a combination of the concepts that we just described for the pseudospectral method and the finite element method. Actually then, but we'll look at this later, this superposition of basis functions will happen inside each element. Very elegant. So we will see this later. So these are some fundamental ways of describing or discretizing wave-like functions that we will employ with the various methods that we will encounter.